Thank you guys all for joining us down here. And I'm going to talk about the asynchronous traffic shaper today. So let's take a quick look. Okay. Clicking the wrong direction. So 802.1 QCR was standardized back in 2020, but in reality, it is only starting to be used today. We're going to talk a little bit about that today. And we're going to, first of all, give an introduction. What is the asynchronous traffic shaper? We're going to talk about some of the differences between the requirements for talkers and switches. We are then going to look at a comparison between ATS and other shapers. We are going to also talk about the interactions with some of those other shapers, specifically with QBV and QAV. And we're going to look at the applicability automotive, how to test, and finally give some recommendations. So that's a fairly big agenda. I only have 25 minutes. I'm not going to be able to talk about all the details. If you want more information than is covered in here, please talk to me. Some of the topics are going to be controversial, which is what makes us interesting. So let's go on. So as I said, the asynchronous traffic shaper was standardized, I should say, in 2020. And then what did it give us? So it was an attempt to create a shaper that did not require time synchronization, but still could provide the guaranteed end-to-end latencies that the industry needed. So in addition to those two requirements, it also provides stream-level granularity. So unlike QBV, which controls things on a per queue level, or QAV, which controls, at least at a switch, the only shaping is at a per class level, QCR provides stream level shaping. It delivers fault isolation, and it makes it relatively easy to add or remove or modify devices on the network. And it makes relatively efficient use of the Ethernet bandwidth. You don't have some of the issues like you have with the time aware scheduler, where you may, in some cases, I'll call it, have to over-provision. With both QAV and QBV, there's some over-provisioning that may be lessened in here. This having been said, like all algorithms, it's got pros and cons. There's no silver bullet, right? So we're going to take a look. So I don't expect anyone to be able to read everything that's in this slide, but this code that's here on the upper left is a Python representation of a generalized version of the QCR scheduling algorithm. And it's generalized because it covers both the end station and the switches. The spec actually defines them in two separate sections. I combined them to try to show what's different. There's actually a section in here that says, if not bridge, do this. So there's an if statement that depends on the behavior of the switch versus the end station. The QCR is applied on the egress ports. So while it is an egress-based algorithm, there is a requirement to have at least one queue from each ingress port for each egress port. So if you have 3 ingress ports going to one egress port, you need to have at least 3 queues. And this algorithm is based on the leaky bucket algorithm, but it's been modified. It's been modified to make it easier to implement on hardware. We'll get into how it's been modified in the next few slides. At a very high level, I want to talk about some of the parameters. So we have this committed information rate, which is basically the bandwidth allocated to a stream. The committed burst size, which is the maximum amount of data that can be held in the bucket. Beyond that, we start dropping data. and the maximum residence time, which is the maximum amount of time between ingress and egress of a frame, which also, if we're going to exceed that, we're also going to start dropping frames. Okay, so that's, again, ignoring all of the details in here, I'm going to try to give some examples. So here's a simple algorithm. The ingress rate and the egress rate are the same. So, when you receive a frame, you can immediately transmit it. You can see that the tokens get accumulated until we transmit, and then, or really it's till the end of the received frame, and then we use a token when we transmit and go again. So it's a very regular fashion, and these are based on a simulation. And the token is really the time delta between the arrival time and the bucket empty list. And so this is my definition of a token for the purpose of these graphs. What happens if we have data coming in at a higher rate than we can transmit? In this case, we've increased the size of each frame such that we cannot no longer transmit at the same rate. So we have frames coming in at a certain rate. The algorithm is going to slow down the rate of transmission. Now you can see that at the time that the frame is received, we're already using up the token, and we're basically making a down payment towards what we have to pay when we transmit the frame. Then we have to pay the rest of it. We have to finish our layaway plan, and once we've accrued enough credit, we have the ability to transmit the frame. Now, these tokens will keep on decreasing until the maximum residence time is reached, at which point we will start dropping frames, because we can't actually keep up with a higher incoming rate than an outgoing rate. Just looking at the opposite example, this is an example where we configured it to allow a higher rate than what's coming in. And what happens here is that we'll just stop accruing the credit. Once we hit the committed information rate, we stop accruing any more credits. So now this is looking at a single stream example. It can get complicated once you begin having multiple streams going at different speeds. So I don't have time to get into that, but we can talk about some of the behaviors and the differences between end stations and bridges. So the end station is considered a simplified version. It's defined in clause 49 of 802.1q. And there are a few things to point out. First of all, there's a single clock. The transmit clock and the scheduling clock, or the arrival time clock, are the same. There is a single scheduler queue per stream. So each stream has a dedicated queue. Then frames output by multiple ATS schedulers need to be sorted. So at the end, we need to sort frames by the eligibility time, which is hard to do in hardware because you need some kind of a priority queue, but in software it's not that hard. Also, in the case of the endpoint, frames are never dropped due to the ATS algorithm. They can be dropped for other reasons. They can be dropped because queues entering are run out, you run out of memory, but the algorithm itself doesn't define any cases in which it's dropped. You're just going to keep on queuing. And I'm going to argue that in end stations, ATS can be implemented fully in software. In fact, I've done it, but that's not necessarily true for bridges, which we'll look at next. So the bridge implementation is defined in a different section of 802.1, specifically clause 8.6. And here we introduce a concept of scheduler groups. The idea of scheduler groups is to reduce the hardware complexity. So you take all of the streams that come from a single ingress port or a single class per ingress port, and you group them together and you add one rule, and that's that the transmission time, once you have a stream that has a given transmission eligibility time, you can never go back. So if stream A is going to be transmitted at 9 o'clock, then stream B cannot be scheduled to transmit at 8:59. It has to transmit after 9. So we also add the ability to support priority reassignment based on a stream, meaning that even if the packet says I'm on priority 5, when we look up the stream, it can say, no, for the purpose of this algorithm, we're going to treat it as priority 4. For the purpose of the algorithm in this node, in this switch, we're going to have a different priority. We can filter out on a per stream basis a maximum length of a frame, the maximum STU, and we can drop frames that would fail to meet the maximum residence time. So, and this allows multiple schedule and transmission selection clocks. You can see there's a clock at the top and a clock at the bottom, but there's requirements for how far apart they can be, both in terms of phase and frequency. So the assumption is the two clocks are kept locked to each other within certain bounds defined by the implementation. So I went into a lot of details here. I think the point here is that there are significant differences between the end station and the bridge implementation, and I've tried to cover some of them. We talked about scheduler groups here, which is where we group all of the streams coming in and put them essentially in one queue from a single ingress port. So there are some implications. The first is, as we said, that the frames are not reordered within a stream group. And so, as I've said before, it means that it may cause delays for streams from other groups within certain bounds. The second is the maximum residence time is shared by all streams within the group. So if we say the maximum residence time is 100 milliseconds from every frame that comes from the ingress port to the same egress port within the same class. So just a very quick example. Let's say we have stream A that's configured to send 1 frame a second, and stream B is configured to send 100 frames a second, and we have a maximum residence time of 100 milliseconds. So what happens if frame A arrives early? If it arrives more than 100 milliseconds early, we would drop that frame because it would otherwise exceed the maximum residence time. We would have to delay it by more than 100 milliseconds. If it arrives within 100 milliseconds of its expected time, then we would schedule it for its expected time, but then the frames from stream B that are 100 times faster come in, they would have to be delayed because they could only be transmitted after frame A because they're in the same scheduler group. So, and that could happen for as many as 100 milliseconds, meaning you could queue as many as 10 frames from stream B after the 1 frame from stream A, and they would all be sent out in a burst in this schedule. Now, I'm not saying it's a typical example. I'm specifically choosing parameters that highlight this, but the point is that ATS gives you a lot of power because it gives a lot of parameters on a per stream basis and a per stream group basis, but you also have to understand the implications of making all those choices in the configuration. So very quickly comparing ATS to other schedulers. Again, we could talk about it for a long time. I am going to say that at a high level, a lot of these are generalizations. There are, for example, here I'm stating that a QBV will typically have a lower maximum latency than QAV. And it's true that in many cases you can come up with a QBV schedule that has a lower maximum end-to-end latency than QAV, but it's not always the case. There are cases where the opposite is true as well. So just treat this as generalizations for the point of this presentation. So looking at this, so time sync. 802.QCR does not require time sync, but it technically has some requirements. You need to specify the maximum frequency deviation. For example, it might be plus minus 100 ppm or plus minus 10 ppm, because those assumptions are made by the schedule. This is similar to Ethernet, where the standard specifies the requirements and there are assumptions made based on that. QAV does require only frequency synchronization. We use 802.1 AS, but we use it really to make sure that everything is synchronized. Everything has to work at the same frequency. You don't really need to synchronize time, you need to synchronize frequency. And in QBV, you need full-time synchronization. Shaping unit, we talked about this. QCR, shapes per stream. QAV, shapes per stream only at the talker, but then at every bridge, it shapes per class, and QBV is per gate. Burst accumulation in QCR, it's within a stream group, at least on a bridge. A QAV, you can get burst accumulation, and in some cases, there have been some failure cases. We can see that you can get bursts that can exceed the buffer size and cause overflows. And in QBV, bursts are allowed while the gate is open. While the gate is open, there's no limitation of how fast frames can be transmitted. So by definition, so while the gate is open, it's essentially a burst. Maximum latency guarantees. I'm arguing that that QBV has the best guarantees. QCR has guarantees as well. I'm arguing that QBV has failure cases that have been demonstrated that cause those guarantees not to be as strong, but I'm also going to argue that even though I'm saying that QAV on its own does not have latency guarantees, if you combine QAV with QCI, the combination of the filtering with the shaping does provide the guarantees. Traffic types, asynchronous supports periodic burst, random, and random with bandwidth time supports different types of traffic. QAV is only good for periodic traffic, and QBV, again, can be used for almost any type of traffic. The maximum latency, I think I've already talked about. I'm arguing that QBV is the lowest, QAV is the highest, QCR is the middle, but again, those are typical, depends on the configuration. Complexity of implementation and configuration is the opposite. I'm arguing QAV is the easiest because typically there's no configuration. QBV is the most complicated because it's coming up with a schedule is complicated. QCR is somewhere in the middle, but because QCR has its own large set of parameters, it's still somewhat complicated. And again, those are all arguable. You can depend on the specific configuration. Interactions with other schedulers. ATS is based on receive time, not transmit status. And what that means is that if something is blocked on the receive, then we're going to queue up the traffic and we're going to transmit a burst. So, for example, when you have the time-aware scheduler, QBV, and you have QCR. QCR will make queue a bunch of frames while its gate is closed, and all of those gates it will burst out when the gate opens. Similarly, with QAV, there's an assumption that QAV is intended to use the highest priority queues, and ATS is intended to use the highest N queues. And the point is you can't have both algorithms using the same high priority queues. And so one of them is going to be higher priority than the other, and those will cause interactions interfering with the normal behavior of the other. Okay, what needs to be tested at a high level? Stream filtering. Are we identifying the stream and all the parameters? Gating. Are we updating the priority or not updating if that wasn't selected? Dealing with multiple priorities. Really, this is the most important is the time, the eligibility time assignment, as well as the information of maximum residence time. And the group eligibility time, if you happen to be in a bridge, that clock offsets are within the bounds, that clock rates are within the defined bounds. Assigned eligibility time that it says properly, it should have said properly compensating for clock offset and processing delay, and also we need to check the behavior when we do dynamic changes. And finally, system and interoperability tests need to be run to make sure this is all going to work in a real system and to validate all the interactions between the ECUs. So how do we validate in a bridge? Typically, we have I'm showing here in the picture one talker, but typically you need multiple talkers communicating to the device under test. In this case, this is a bridge, communicating to the listener. And if you need to test multiple scheduler groups, then the multiple talker need to be connected to the DAT. The traffic needs to be sent at very controlled. So the talker needs to have control of exactly when each frame is sent. And the listener needs to be synchronized to the talker so it can evaluate the behavior of the algorithm within the DAT. And so you can use a device that connects to both sides of the DAT to perform these tests. Similarly, to test an end station, you need to test the QCR implementation, but now you need to use a software traffic generator. It can be either the normal software that is generated on that end station or some fake generation, but you need some kind of a traffic generator. At Keysight, we have our own test traffic generator that we've used in other shapers, and we are planning to do the same thing here. And then typically on the external side, you need to test what actually gets transmitted, assuming that this is the physical port. And finally, in order to test for the valid frequency deviation, you need some kind of an accurate time reference so that you can actually measure this. That's at a high level. So I work for Keysight, and we, of course, make test equipment. We provide the ability and solutions to test many of the TSN features. Basically, almost anything that you can think of in TSN, we've got solutions for. And so I got into doing this by implementing ATS for test solutions. And these are kind of my recommendations from the work that I've done. So first thing to note is that commercial implementation is just starting to come out. There have been many experiments with ATS, a lot of proof of concept, but in terms of support in silicon and software, it's just starting to come out and is lacking in many cases. There is also limited community knowledge, which is one of the things that really convinced me to do this presentation. I'm not going to say that I know everything or that the ATS is the best, but I at least want to educate people and say, hey, it's interesting, it solves some problems, that it provides another solution in the tool set. Maybe it's an appropriate choice. And again, it has potential benefits and limitations, and you have to weigh those. And I covered some of them. And it's recommended that you do take a serious look at it, see does its benefits solve the problems that you have. And at the end, the only way to know how things should work is you need to run a simulation to model the behavior under both the ideal and the unexpected conditions. And everything, in order to know it works, has to be tested. And we're happy to help with that. And that's it. Any questions? Yeah.
Thank you, Alon, very much for your presentation. I do have actually a question. What kind of applications do you think the asynchronous traffic shaper is best?
I think asynchronous traffic shaping works well where you have a mix of different types of traffic and speeds. Where the limitation of QAV and QBV is in QAV you have exactly two classes. In QBV you have so many queues, and yes, it can work. The individual stream can have many different parameters, but QCR has advantages when you have a lot of different types of traffic that where having the ability to control things on a per stream basis has a lot of advantages. And I do think that in many cases it's a compromise between QBV and QAV. You get it's not necessarily quite as low latency as the best case QBV, but it is better than QAV.
All right.
Yeah.
Thank you.
Yeah.
There are some questions.
Yeah.
Hi, thank you. Eric Parra here, Technical Engineering. Hi, Alon.
Hi.
So, with regards to the test suites and how to test, this is purely out of curiosity.
Yeah.
Is there any kind of standardized or use case-based test scenario where you look at zonal architectures and there's this kind of worst-case traffic that would potentially come in real world, and this is part of the test suite that you're using to validate the ATS implementation?
So the quick answer is there's no standardized one, because the worst case is, for better or worse, is application dependent, right? We can tell you what some of the things that would cause a worst case, but we can help identify I'll call them what are the corner cases, but we cannot define a worst case test case until there is a definition of a standardized use case. So if someone says, this is how we're using this algorithm, let's say this is I'll call it a typical use case for QCR, let's say in a vehicle, for example. I'm not going to get more specific. Then we can take that and say, and here's a standardized use case, and we can work through the standards organization. But right now, I'm not aware of either one existing.
Okay, because in light of IEEE Open Alliance, what we're doing here, standardizations and stuff, probably that kind of corner case identification would be useful, right?
Absolutely, and I think this will follow. I think the test cases will follow the work that's being done in the Open Alliance.
Okay.
Thank
you. One last question. Can closer to the microphone.
Yeah, wow, I could hear myself. Okay, this is Bernie from NXP. So so basically a little bit on the discussion you had before this one, which is basically, yes, you have QAV and you've got QCR, which basically both need a high priority traffic class. And of course, they're probably going to be both enabled at the same time on the same port. The question I have is on QCR, like how many traffic classes are we talking about supporting? Because it depends on, yes, all the streams could go into a scheduler group, but that only represents one traffic class. So how many traffic classes do we actually see needed?
So with QCR, again, there's no definition. Unlike QAV, where it's defined that there's 2 traffic classes, in QCR there is no definition of how many traffic classes there are. Now, of course, you can't have more than 8 because you only have 8 queues. In reality, I think most use cases will probably get away with 1. I think it'll be more like QAV, where you may have 2, again maybe 3. But again, this is my guess. It's not based on any data.
Exactly. I'm in the same position as well, because I'm going to say, okay, maybe 2 traffic classes for QCR, but then it's always a question of scalability because you got a lot of queues.
Yes.
Right? Because depending on how many ports you have on your switch, for example, that's that many queues times number of traffic classes.
Exactly, and it becomes an n-squared problem because you need effectively a queue per ingress port. So your number of ports queues, then as the number of ports in your bridge grows, assuming that you have full meshing, you need n-squared times number of classes queues. So again,
exactly. And how well does these different traffic classes interact with each other, which is the other big problem.
Yes.
Which is like, that's why I'm a little skeptical.
And a lot of that also comes in again, and there's an assumption that all these different queues use different hardware. The whole question of how do you architect your switch such that you can minimize that complexity, and that's all its own art form. And okay.
Thank you, Alon. Okay. So in case you have further questions, use the speaker's corner after the session. Thank you very much, Alon.
Thank you.